So what I want to say is like now can I say that this ring is a product of fields?
Okay, so let's start. Let me share the screen.
No, here it is. There is nothing about noisier in the scene. No.
Okay.
No.
So today we'll solve Gate 2023 questions from real analysis. So these are the basically questions from measure theory. So we will solve question number 16 and 17. Okay, first let me start the question number 16.
So after that.
Let's wait.
As a ring, it is not noisy, right? It has a vector space with other case. Right? Okay. Right.
Okay, so today we will solve Gate 2023 mathematics question. This is question
One more
number.
question. Like, see, there is something called general position. What does that mean?
Number 16. It is question from real analysis. So let's see. Let
No,
A.
see, have you
This
seen
is
that
a
in that paper?
non-measurable set with
the
respect to
bracket,
the measure
on
R.
orbits of
And the following two statements
So
are
there he says like
saying that if M is all points in
orbits of
the N,
the
the set of non-measurable sets such that X is irrational. Then
So
M
there
is saying that M is measurable.
he defines something or
And Q is saying that the boundary of N has positive level outer measure.
Then he is saying that them being
Then
general
four options
position,
are
he is
given.
giving some definition for
It's
it.
saying that both PQ are true, P is false, Q is true, P is true, Q is false, both PQ are false. So you have to check PQ are true or not, or which one is true or that is false. Okay, so in order to solve this problem, this is the NPTEL reference. This is a question from this is the measure theory on the real line.
Yeah, but I don't know what exactly he means by here.
Okay, let's see. So on R, so for R,
Okay,
on
did you see
a power
that?
set of this is denote the power set of R. So it's called all subsets of R. But this is a sigma algebra, and so this sigma algebra is all sets in this sigma algebra are not Lebesgue measurable, right? So they are non-measurable sets. So let's denote this L of R. This is called the Lebesgue measurable subsets of R.
Oh, you take I to be R, like you are just limited on this V of Q. There is no V of Q. This is the relative case. You just see the next lemma, like how
Subsets of R. So this is a strictly content in this power set of R. Means there are sets which are not Lebesgue measurable in R. So this is one such set. This we are calling this is non-measurable set on R. Non-measurable set on R. So this is with respect to Lebesgue measure. We are dealing here with Lebesgue measure. With respect to
no, you just forget you just take R elements to be general position, V given of finite elements of dimension. See, I is actually an ideal which is fixed to start with.
So what is first option is saying that M, which is the all x in n, so the x is irrational. So M, it is all such x is in n. Okay, so let me tell that this is a means non-measurable set. It has a construct set.
Oh, you
So
that
you can construct a set which is not Lebesgue measurable on R. You can do it on R.
There's the next lemma is
There is a more general result that for any positive measure set, there exists a non-measurable set inside that. That you can show also. So, means the explicit example is little bit difficult for non-measurable sets, but there is a construction for non-measurable sets. So that M is x is in n, so that x is irrational. Okay. So you have to check that this is Lebesgue measurable or not. So what is this basically? This is basically n intersection Q complement, right? What is Q? Q is the set of rational numbers. So this is this, right?
Okay. So another question is I
That is not the set of.
yeah, it should be yeah.
Rational number. Is 0. Take all such this basically R minus. So this is this, right?
So if okay, where is it?
That is not the set of rational number in R. Q complement. This is just basically R minus Q. Set of irrational numbers.
So an element, see, if you just one more. Like
So to check that M
you
is
are
Lebesgue
taking
measurable or
D,
not.
right? And he is taking this. If you read
So
the
let's
first
first note that
like he is saying B is
this
thing and
you
W is
know that
we may arrange them
Q
B not
is
in
Q union Q
that
complement.
this D minus
This is whole R,
whole
right?
modular.
This R you can write as rational union and irrational, right? Q and Q complement. So N you can also write. So then
This is 2.4 is which is CFM is that
then you
if
can
have
write N
the ED plus
N
ED
intersection basically Q. Take all such rational which are in N union N
See here
intersection Q
what I
complement.
understood by general question is like
So this is a set where all such irrational which are in N.
so that is that
Let me call this
see there is that lemma right
Suppose A
where you can write like
union,
D not
this is
D1.
M basically, right?
You can write
Or let me
we find some T1 to
this
T
is
D such as D
N
not plus
intersection
T1
Q and this is M. So this
Ah.
is basically
So
M
I
as the
understood
N
that is what
intersection Q complement. Right. So you have to check that M is Lebesgue measurable or not. So first there is one fact that user let me result this is
okay yeah
the Q is Lebesgue measurable
right
and the Lebesgue measure of Q is 0, right? So as you know Q is countable, basically you can prove that countable set as Lebesgue measure 0. So this is more general as so this is just as Q is countable, so that's why it is Lebesgue measure 0. And every measure zero set is level measurable. Right. So Q is level measurable and it has measure zero. Okay. Now any one, and there is a, so this is result 1 and result 2. So saying that R is means level measure is complete. Level measure is complete. Means what is this saying? That every subset of measure zero set is again level measurable. So it is saying that every subset of measure zero, of level measure zero, level measure zero is again measurable, level measurable basically. Measurable means level measurable.
So that's why you add this, how you add this. Like the B0, W0, W1, WD minus 1, you do that thing. There is no WD there, right?
And it should have level measure zero, right? And it has also the measure zero. So here what we have,
B0, W0.
so note that this N intersection Q now. So we use this to result. Note that N intersection Q, this is a subset of Q, right? So N intersection is a subset of Q, and as measure of Q, you know this is 0.
Yeah.
So which implies that as this is a subset of measure zero set, which implies that N intersection Q is level measurable.
That I have to find G is there.
And what we will get? That also measure of N intersection Q is also 0. Right? Because this is a subset of a measure zero set, so it has a measure 0. So we get what we have got, that N intersection Q is level measurable and it has measure 0. So now suppose, but we have to find what about M. M is N intersection Q complement. Okay. So now suppose N intersection Q complement is level measurable. Then what will happen? So we will prove the contradiction. So
what could be this context like? What G00?
Suppose this is level measurable. So let me write another result. So what it is saying, that countable union of measurable set is again measurable. Or
Right.
so it is saying that countable union of measurable subset is again
Audio you cannot hear. Let me play. If there is any problem, you can tell.
measurable. So we will use this result. So as this is true for countable sets, so obviously true for finite union of sets, right? Because these are again countable, you can say, right? So finite union of measurable sets are again measurable. So note as N is basically how we have written N intersection Q union n intersection Q complement. So we have what we have? N intersection Q is measurable, right? What we have shown above, as shown above. And by our assumption, N intersection Q complement is also measurable. Now we will use this result. So union of these two measurable set again will be measurable, which imply N union Q, N intersection Q union N intersection Q complement is measurable. Right? So this is by the result 3. Let me call it. By result 3. So which implies that n is measurable, because this is n, right? N is level. But this is a contradiction, right? But this is a contradiction. So means our assumption is wrong. So therefore, what is our assumption? So what we have assumed? So we have assumed that n intersection Q complement is Lebesgue measure. So this is our assumption. So this is wrong. So therefore, n intersection Q is not measurable. So therefore, our assumption is wrong. So n intersection Q complement, which is basically M, is not Lebesgue measurable. Okay. The first option E, P is false basically. M is not Lebesgue measurable. So this is false. So now let the option means Q. It is saying that boundary of n has positive Lebesgue outer measure. Right. Okay. So let me denote this delta n. This is basically I am denoting at boundary of n. Boundary of n. Right. So you have to say that boundary of n has positive Lebesgue out measure. It is saying that. So m star delta n, this is the outer measure of boundary n. Outer measure of del n. Okay. So you have to show it's saying that outer measure of del n is del has positive Lebesgue measure. So suppose not. So we let do this by contradiction. So suppose m star of del n has measure 0, right? So what will happen? As I am saying earlier that every measure 0 set is Lebesgue measurable. So which implies as this has measure outer measure 0, which implies del n. So this is the fact that if it has outer measure 0, then it is a Lebesgue measurable. So del n is Lebesgue measurable, which implies, so if the assumption is true, means we have assumed this is true, which implies del n is Lebesgue measurable, and every subset, because the Lebesgue measure is complete, every subset of it is also Lebesgue measurable. So which will be del n and all its subsets, and all its subsets are level measurable. Right. Okay, now so we have assumed, so this is our assumption. Let's check how you can write n. So n, this you can write any set, this is true for any set, you can write it as a interior of n union is set. So let me write it what these are, int n and a, right, n equals to this, where int of n, so this is basically interior of n, set of all interior points of n, means set of all interior points of n. Right. So interior point means for every point there is a neighborhood which is contained in n. Okay. So any set you can write as a interior union where A is a, what is A? So this is a subset of del n, right? So this is the natural fact. Any set you can write as a interior of n, union is set which is a subset of its boundary. What is boundary? Here basically, let me write. So this is basically the n closure minus interior of n. Right, closure minus interior is the boundary. So like, let me give an example. So this you can always write. Suppose this is 0, 1. What is so let me call this is x. So what is interior of x? So this is 0, 1. And what is boundary of x? This is 0 and 1. So how you can write x? This is 0, 1. You can write basically as 0, 1 union phi, right? There is no point. So this is basically interior of x union a set which is a subset of boundary, right? Here it is phi. This is phi, subset of del x, right? And similarly for let take x to be closed 0, 1. So what is the interior of x? Interior of x will be 0, 1. And what is boundary of x? This is 0, 1, right? So then you can write this 0, 1, which is x. You can write 0, 1 union these two, right? So this is interior of x union a set which is a, here it is 0, 1 boundary of x, right? So in general you can prove this. Any set you can write as in interior of that set union a subset which is a subset of its boundary, right? Okay. So we'll use this fact to prove our result. Okay. Now note this, what is interior of n? So this is one result. Let me write. That for any given set, S, interior of S is always an open set. This is basically by definition you can easily prove that interior of S is always an open set, right? So this is a one result. And result 2, what let me write that open seat is measurable always. So what is open sets are Lebesgue measurable. Lebesgue measurable. Right. So what we have here, interior of n is an open set.
Okay.
Interior of n is an, because interior of set is an open set, is an open set, which implies int n, so interior of n is Lebesgue measurable. Right. Okay. And now, so n, what we have write n equals to int n union a. And what is a? This is a subset of delta n, and where we have assumed the delta n as measure 0, and what we get, delta n and all its subsets are also Lebesgue measurable. So in particular, a is also Lebesgue measurable, right? And note a, which is subset of delta n, and has all subsets of
Now, can you hear it, or is this still not fine? Not clear. Okay.
delta n are Lebesgue measurable. Which implies a is measurable also, right? Because the Lebesgue measure is complete, which I have said earlier. So a is measurable, what we have got? Int a is measurable, a is measurable, and we have write down earlier that countable union of measurable sets is measurable. So basically finite. So finite union is also measurable, which implies int n union a is Lebesgue measurable. But what is this? Int n union a. So this is basically n, right? So therefore it is saying that n is measurable, which implies n is Lebesgue measurable. But this is a contradiction, right? This is a contradiction. Because we know that n is not Lebesgue measurable, because n is by definition it's non-measurable, as n is non-measurable. So our assumption is wrong. So what is our assumption? So our assumption is that, our assumption is that m star del n is 0, right? So we have assumed that m star of del n is 0. So this is our assumption. So this is wrong. Our assumption is wrong. implies that outer measure of del n has positive level, right? Which implies it is means not 0, so outer measure of boundary has positive outer measure. So this is the second option Q. So boundary of n has a positive level outer measure, so this is correct. So P we have got, it is false and Q is true. So which option is correct? P is false and Q is true. So option number B is correct. Okay.
Hello. Hello. So you cannot hear the video, or can anyone reply? Okay. So you're saying there is some problem in the video. Okay, let me join from. Okay, so any doubt from this question? Let me join from other. Any doubt with this question? No. Okay. Second, tell me, can you hear the video or not? Let me play it again. If you cannot hear it, then I will. Can you hear it now? You cannot hear the audio of the video? Now can you hear it or not?
Okay. So let
Now? No. Okay. Should I rejoin? Means I don't know why you cannot listen the audio.
we will solve Gate 2023 mathematics question. Okay. So today we will solve Gate 2023 mathematics question.
You cannot listen the audio? Okay, audio. Okay, fine.
This is question number 17. This question from real numbers. What it is saying? For k in n, let Ek be measurable subsets of 0 1 with Lebesgue measure 1 over k square, and E is this intersection from n equals to 1 to infinity union k equals to n to infinity Ek, and F which is union a equals to n equals to 1 to infinity intersection k equals to n to infinity Ek. Right. Then the two statements are given. Saying that P, which is Lebesgue measure of E, is equals to 0. For E, it is saying that Lebesgue measure is equals to 0. And Q is saying that Lebesgue measure of F is equals to 0. Four options are given. Both P, Q are true. Both P and Q are false. P is true, Q is false. Q is true, Q is false. So in order to solving this is the NPTEL reference for this question. Okay. So two sets are given, E and F. We have to say that Lebesgue measure of E and F are 0 or not. Okay. So what it is first given for K belongs to natural number. Ek, these are the Lebesgue measurable subset of 0 1.
Monokumar, you can mute yourself.
They are measurable. And measure of Ek, it is saying that 1 by k square. Right. And how E is defined? So E is basically intersection n equals to 1 to infinity union k equals to n to infinity Ek. And what is F? F is basically union n equals to 1 to infinity intersection k equals to n to infinity Ek. So this is basically called the limb soup of Ek. So this is limb soup of Ek, and this is called limit. We have to find the Lebesgue measure of E and F. So first we have to check that these are Lebesgue measurable. Okay. So let me write one result. So this is one result, that standard result from measure theory. That countable union and countable intersection of measurable sets are again measurable. Right. So what is E? E is basically first we have taken the countable union, then we have taken countable intersection, right? And F is the similarly basically the other way. It's in first we have taken intersection k equals to n to infinity, then we have taken union n equals to 1. So therefore E and F are Lebesgue measurable. So now we have to find the Lebesgue measure of E and F. So first let's try for E. So M of E, basically this is the Lebesgue measure of Lebesgue measure of E. So what is this? So this is basically M of, this is not union, this is intersection n equals to 1 to infinity, union k equals to n to infinity, ek. Right. Now this is basically the intersection. So this you can always write, because as, so note that this is always true. Measure of union k equals to n to infinity, because we are taking intersection. So note the intersection n equals to 1 to infinity, union k equals to n to infinity, ek subset of this one, right? Because left hand side you have taken intersection for n equals to 1 to infinity. So when we take the intersection, the sets become smaller, right, of this. So this is easily, you can check that this is true. So as measure by monotonicity of measure, so this will be true. So this is for all n, right? You can do it for all n. And now what is this? This is just, now so here we have used monotonicity. So what is this of M? So it is saying that, so let me write it here. What is monotonicity of M? What it is saying? If E is subset of F, then M of E is less than M of F. Right, so this is called the monotonicity of measure. So this is this one. So what we have, M of E, we have got this one. Now there is also one result, subadditivity of measure. What it is saying? So this is, let me write it. If this is M of this countable union, you can write less than equals to sum n equals to 1 to infinity measure of ek. So this is called the subadditivity of measure. Subadditivity of measure. Okay. And this is true for all n, right? Because this does not depend on n. And what is the measure of ek? So this is the k equals to n to infinity 1 by k square. Right. So what we have got? So measure of E, so therefore measure of E
Not audible again. Let me play it again then.
is less than summation k equals to n to infinity. Okay. Okay.
Can you hear me?
For n equals to 1 to m of f. Also one does not depend on okay, and this is true for all n, right? Because this does not depend on n.
Sir, actually the audio
And what is the measure?
is not playing.
Right now? It is still not playing?
Of e
Right?
Screen is visible, sir, but we are not here. We are not able to hear the audio.
1 by
Means
k
right now, means I can hear, that's why I am saying. Right now?
So what we
But
have
we
got?
are can't.
Oh. I don't know what is happening.
So
Means few, yeah.
1 by k square.
Now?
Right. So what we have got? So measure of E.
No, sir.
So therefore,
Okay. Means I have nothing to do, means I just play the video. Cannot change anything here.
Sir, actually in a Google Meet we can't hear the audio.
But in the last time it's
But
fine.
Oh, okay. But in Zoom call we can clearly hear the audio, sir.
Okay. Okay, let's do it today. From next time I will do something.
Okay,
If there is any doubt, you can ask me after this.
measure of E is less than summation k equals to n to infinity 1 over k square for all n. Right. And what is this right hand side? So as summation k equals to 1 to infinity 1 over k square. So this is because this is the you can test that this series is convergent. So n to the power p where p is bigger than 1. So as this series is convergent, which implies the tail part of this series will goes to 0, which implies for k equals to n to infinity of 1 by k square is goes to 0 as n tends to infinity, right? Means tail part of this series going to 0. So this is the so this is saying that whenever this series is convergent, so this is the tail part of this series will goes to 0, right? So we'll use this, that as n tends to infinity the tail part is going to 0. So as measure of E is less than summation k equals to n to infinity 1 by k square for all n. So letting n tends to infinity, what will happen? Right hand side will goes to 0, right? Summation k equals to n to infinity 1 by k square will goes to 0 because this is the tail part of a convergent series, which implies measure of E is 0, right? So you have got that measure of E is 0. So the first option is basically correct. Lebesgue measure of E is equal to 0. Okay, so this is basically correct. Now let's check the next option. Lebesgue measure of F is equals to 0. Okay, this can be done by similarly. So let's check. What is F? What is F? M of F basically M of union n equals to 1 to infinity intersection k equals to n to infinity ek. Right. So this again by subadditivity what you have done earlier. So this you can write summation n equals to 1 to infinity measure of this intersection ek, right? So this is by subadditivity. Subadditivity of M of this measure. Now what is the measure of this set? You have to find the measure of this set. Okay. So now here we need one observation. So now note this observation here is crucial that intersection k equals to n to infinity ek. This is basically subset of all ER for R greater than n, right? So what is this say? So because this is the intersection from, so like this. So this is first En intersection En plus 1 intersection En plus, let me write it in red. So why this is true basically? So this is En intersection En plus 1 intersection En plus 2 intersection dot dot dot. So obviously because this is the intersection, this is a subset of some ER for any ER greater than n, right? Because it will, the whole intersection obviously is subset of any set, right? Any ER greater than n, right? So this is obviously true. So therefore what will happen? So then by, so this is for all R, right? For all R equals greater than equals to 1. So this is true for any. So now what will happen by monotonicity? So from here by monotonicity. Measure of this set k from n to infinity ek will be subset of measure of ER, right? And this is for all R greater than equals to n. And what is this? Measure of this. So this is, sorry, less than this. Because this is measure. And what is this? This is 1 by R square. Now again as earlier we will take R tends to 0. So take R tends to infinity. Because this is true for all R. So we can take R tends to infinity, then what will happen? Then measure of intersection k equals to n to infinity ek will be 0. Right? So we have got that in measure of this set is 0. So therefore what will be the measure of M? F. Therefore measure of F, which is basically less than measure n equals to 1 to infinity, measure of intersection k equals to n to infinity ek. And individually each set has measure 0, so the total is measure 0. So what we have got? M of F has also measure 0. So therefore what is this option? Q. Lebesgue measure of F is equals to 0. So here both the options are correct. Both P and Q are true and both has Lebesgue measure 0. So therefore both P and Q are true. Option number A is correct. Okay.
Okay, so any doubt from this one? From this question, any doubt? Yeah, I will upload these videos in the YouTube. You can watch it there. From the next time, I will say something. I will do something that so that you can hear it properly. Yeah. Okay, so let's stop for today.